You have seen that when a plane intersects the nape of a cone at any point other than the vertex, such that the angle beta between the plane and the axis of the cone is greater than angle alpha between the axis and the generator of the cone, but less than 90 degrees. The resulting conic section is an ellipse. We better know an ellipse as an oval shape. Now, let us recall the formal definition of an ellipse. Consider two fixed points, F1 and F2 in a plane. Now consider points P1, P2 and P3 such that the sum of their distances from F1 and F2 is equal. Then, the closed curve passing through all such points is an ellipse. Thus an ellipse is the set of all those points in a plane, the sum of whose distances from two fixed points is constant. Remember that an ellipse is formed only by those points whose sum of distances from two fixed points is constant and greater than the distance between the two fixed points. The fixed points in the plane are the two focus points of an ellipse, jointly called the foci. The line segment passing through the foci of an ellipse and touching its sides is called the major axis of the ellipse. The 2 points where the major axis touches the ellipse are called the vertices of the ellipse. The midpoint of the major axis, or the midpoint of the line segment joining the foci of an ellipse, is called the center of the ellipse. The line segment passing through the center of an ellipse and perpendicular to the major axis is called the minor axis of the ellipse. A line segment joining the center of an ellipse to either of its vertices is called a semi-major axis. Clearly, a semi-major axis is half of the major axis of an ellipse. Similarly, a line segment joining the center of an ellipse to either of the endpoints of its minor axis is called a semi-minor axis. Clearly, a semi-minor axis is half of the minor axis of an ellipse. If the length of the major axis of an ellipse is 2a, the length of each of its semi-major axes is a. Similarly, if the length of the minor axis of an ellipse is 2b, then the length of each of its semi-minor axes is b. Also, if the distance between the two foci of an ellipse is 2c, the distance of either focus from the center of the ellipse is c. Let us now derive a relationship between length a of the semi-major axis, length b of the semi-minor axis, and distance c of a focus of an ellipse from its center. Consider a point P at one of the endpoints of the major axis of an ellipse. The distance of point P from focus F1 is equal to the distance F1 O plus OP. Since F1O is equal to C and OP is equal to semi-major axis A, PF1 is equal to C plus A. Also, the distance of point P from focus F2 is equal to distance OP minus distance OF2. Since OP is equal to A and OF1 is equal to C, PF2 is equal to A minus C. Thus, the sum of the distances of point P from foci F1 and F2 is equal to 2A. Let this be equation 1. Now, consider a point Q at one of the endpoints of the minor axis of the ellipse. The distance of point Q from foci F1 and F2 is given by QF1 and QF2. In right-angled triangle QOF1, hypotenuse QF1 square is equal to QO square plus OF1 square. Since QO is equal to semi-minor axis B and OF1 is equal to C, we get QF1 is equal to under root B square plus C square. Similarly, from right-angled triangle QOF2, we get QF2 is equal to under root B square plus C square. Thus, the sum of the distances of point Q from foci F1 and F2 is equal to 2 into under root B square plus C square. Let this be equation 2. Since both points P and Q lie on the same ellipse, by definition, the sum of their distances from foci F1 and F2 must be the same. Substituting the values of PF1 plus PF2 and QF1 plus QF2 from equations 1 and 2, we get 2a is equal to 2 into under root B square plus C square. On simplifying, we get C is equal to under root A square minus B square. Equation 3 gives an important relation between distance C of a focus of an ellipse from its center and its semi-major axis A and semi-minor axis B, and helps to understand some special cases of an ellipse. If distance C of a focus of an ellipse from its center becomes 0, then the two foci overlap each other. Substituting the value of C as 0 in equation 3, we get A is equal to B. Thus, if C is equal to 0, the lengths of the semi-major axis and the semi-minor axis of an ellipse become equal, and the ellipse becomes a circle with its foci as the center. If distance C of a focus of an ellipse from its center becomes equal to its semi-major axis, then the two foci become its vertices. Substituting the value of C as A in equation 3, we get B is equal to 0. Thus, if C is equal to A, the length of the semi-minor axis of an ellipse becomes 0, and the ellipse becomes a straight line.